Let me start today with two books I definitely want to do with Brouwer at some point, and I think they're very good. I just got them new. They arrived yesterday or the day before yesterday, I don't remember. The first one is Burke and Medina, Classical Field Theories, a Student Companion. So very much excited for this book. It seems really interesting. And let's see what it covers. It covers Lagrangian and Hamiltonian formalism. So you see it's divided up in days. So it starts with Lagrange function and the action. It does the functional derivative, which honestly I don't see a lot in text. They kind of always take it for granted. Even Taylor doesn't really do it properly. Day 3 is already the Hamiltonian formalism. We have Lagrangian approach to scalar fields and Hamiltonian approach to scalar fields, and then we immediately go to space-time symmetries, Lie groups, Lie algebras, and their representations, where we have conserved currents, where we have classical mechanics. We see Noether's theorem being proven. We see representation theorem for Lie groups. We see the Galilean group. Then we go to Minkowski manifolds, Minkowski spacetimes. So we have representation of the Lorentz group. Then we go to relativistic field theory, where we have special relativity and dynamics of particles, Maxwell's equations, and dynamics of fields in the vacuum. The Lagrangian formalism for electromagnetic fields and relativistic matter fields. Then we come to differential geometry, where we see things like connections on a manifold, parallel transport, curvature and torsion, and applications to cosmological spacetimes. Then we come to gauge field theory, gauge invariance, Yang-Mills fields, spontaneous symmetry breaking, standard model, and then fiber bundles. So it really goes into quite advanced stuff. This is already grad stuff. General theory of relativity, gravitational waves, scalar field theory in gravitation, spinors, coupling of electrodynamics to gravitation. So all very cool stuff. Alternative relativistic field theory, alternative electrodynamic theories, alternative theory of gravitation, string and brane theories, subsymmetric field theories, and then finally beyond least action path integral formalism to quantum mechanics, where it deals with the path integral approach to quantum mechanics. So very excited for this book, definitely. So it really starts off with a story. So there's a story running through the book, so it's definitely a very niche book. But it does go into the math. It does also have exercises like exercises for you to fill in the theory. I think this is a beautiful book. Very much a niche book, but very beautiful. I'm very excited to do this book because it looks like a labor of love. It looks like it's not something that classes will use, that will be sold all over the world. This is something, incredibly niche that I think is only for the people who really appreciate these kind of books. So yeah, I would absolutely love to do this book. So what do you need for this book? You need to know, I guess, Hamiltonian and Lagrangian mechanics quite well. So definitely on the level of Taylor, the level of Mann or Lemos is probably advised. You probably need to do, you probably need electrodynamics, so that means stuff like Maxwell's equations, so that means stuff like Purcell. Your math should be good. It's going to use group theory, so you should be comfortable with math abstraction. So yeah, the book is it's quite heavy. The exercises don't look that difficult though, so it's not like it's an insane book, but it covers a lot of beauty. So yeah, That's 1/3 of the video spent on this book, but I am just so excited to get this book and to start working on it. So it's extremely beautiful. The second book, which I'm even more excited for, is this beauty, Esposito, Marmo, and Sudarshan, From Classical to Quantum Mechanics. The problem, I often brought it up with Brouwer in our conversations, but the problem I have with quantum mechanics books is that they kind of deal with quantum mechanics as an a priori theory. They give you the equations, they give you the axioms, they tell you this is Schrödinger's equation, now we're going to solve it, now we're going to interpret it, but nobody ever tells you how they got Schrödinger's equation, why we would find such an equation, why we would propose such an equation. They can't, of course, a book like Griffiths or even the books I like Hannibus or whatever, they can't do that because you lack the tools to appreciate these kind of things. It comes from very deep understanding of classical mechanics, so they cannot do it in any way. But this book tries to do it. So it starts off part 1 from classical to wave mechanics, where it starts off with experimental foundation of quantum theory. They seem to be rather brief about it, so it's only 41 pages. Then you come to classical dynamics, where they immediately start getting into good stuff like Poisson brackets, symplectic geometry, Hamilton-Jacobi equations, Hamilton principal functions, so geometrical optics even. So definitely you need to know Mann or Lemos or those books pretty well to appreciate this. Otherwise, I think it's a bit too brief to really get it. And then we go to wave equations, wave mechanics, from classical to wave mechanics, uncertainty relations and application of wave mechanics, introduction to spin, perturbation theory, then immediately to scattering theory. Then the part 2 is Weyl quantization and algebraic methods, where they cover Weyl quantization, harmonic oscillator and quantum optics, angular momentum operators, algebraic methods for eigenvalue problems, from density matrix to geometrical phases, from classical to quantum statistical mechanics, Lagrangian and phase space formulations, Dirac equation and no interaction theorem, and that's the book essentially. So I'm also very excited to do this book. I'm very excited to do it with Brouwer because I know he will like this. I know he likes this kind of stuff. But you really need the prerequisites. It's you need to know classical mechanics, even graduate classical mechanics on the level of Lemos very well to be able to really get something out of this book. Because the book is quite heavy going immediately, so it really expects you to know all this stuff. But yeah, it all seems to be there. Everything is there basically. So yeah, it seems to be very comprehensive in what it covers. And I've been looking for a book like this for a long time. Like not many books cover this. The usual quantum mechanics books, like the usual books like Griffiths or even Sakurai or Shankar, they just give you the axioms, right? And they kind of try to motivate it, but they don't tell you where it comes from. So they don't tell you this story. There's also quite a number of history books that I know, like books on the history of quantum mechanics, and they know the story, but they're not pedagogical. So they don't really tell you where it comes from. They don't really tell you it's in a theoretical concept. They just tell you the history, and they kind of expect you to know the math already, or the physics already, rather. So I've been looking for a long time for a book to tie the two together in a reasonable story. Assumed, of course, that you know quite a lot already of classical mechanics and electrodynamics. Assuming that you know all of this stuff, is there a story introducing both quantum mechanics and the history of quantum mechanics in one go? and yes, there is this book. So this is here because Mirror might be wondering, this entire video is just going to be about two books, two physics books. Why do I care? Well, see here, this is something that we talked about. These are rigged Hilbert spaces. You see Gelfand triples. We see the Fourier transform. So yeah, the book is already quite mathematical as well, which is supposed to be, because this is about wild quantization. This is about the background of quantum physics, and whether physicists like it or not. Whether physicists like it or not, quantum mechanics is a mathematical theory and is best understood, vastly best understood, in the language of function analysis. Whether that language is from von Neumann in his book, where he basically defined Hilbert spaces in the first time. Hilbert spaces were defined for the first time in von Neumann's treatise by von Neumann. But he didn't do rigged Hilbert space. He didn't do distribution theory. He didn't like Dirac delta function, or whether this rigged Hilbert space approach, which does the Dirac delta function properly. You need the language of function analysis for this to appreciate quantum mechanics the best. Physicists don't like this, because physicists often want to get to the physics fast and don't really care about the mathematical theory behind things. So they try to take shortcuts, but it is often true that mathematicians are like expanding on a physical theory without there being any need for it. But in this case, in quantum mechanics, I think there is need for it. The physics makes much more sense with if you know function analysis well. So yeah. That's basically my rant on physics education as a whole. So yeah, very excited to work through this book. Very excited for Brouwer to work through this book with me. I do want to talk about one last book though, a very, very nice one. And it's this one. It's Visual Group Theory by Carter. And I love this book. It's extremely good book. So it is a group theory book, and it is completely non-rigorous. So it's completely visual. So Crimson, if you're still here after the two physics books are introduced, this book is for you. This is a book you will love. Perhaps not anymore, because you basically know all of it already. But I think, it's a book that maybe you would have loved at some point. So it really starts from scratch. What is a group? And it doesn't give you the axioms direct, and it doesn't even do like Anderson, where it does it with symmetries. It really works with graphs and visualization. So it goes quite far. It goes to Stillov theory, it goes to Galois theory, the fundamental theory of abelian groups. So it goes quite far. And look at the exercises, like they have toys, and then the exercises are basically, yeah, completely non-rigorous. A math book would never have this. Even a book like Anderson, which I love, would never have this kind of thing. So the book is very practical. It really is about the intuition of group theory as opposed to formal rules. So it is about games like this. So this reminds you of Pinter, I guess, but it is really Pinter to the extreme. So very beautiful graphs. You see here the graph of a alternating group, which is a dodecahedron. And the alternating group is the group of a quintic equation, which is unsolvable. So basically this links the dodecahedron to unsolvable equations. There's this chemistry here. There's dances. Very neat stuff. You have Cayley's theorem. Yeah, this is an amazing book. I'm almost out of time, but this book, I would not recommend it as a main book, of course. If you're in a class, you're teaching a class or taking a class, this is not your main book. But as a side resource, or even as bedtime reading, beautiful, absolutely recommended.